603 kilometers per hour. Take a second and picture that. At that speed, a train can cover the length of a football field in less than a second. The view outside the window would not slowly pass by. It would smear into one long blur. This is maglev, short for magnetic levitation. And the first thing that makes it feel so different is not just the speed. It is what you do not hear. There is no familiar clatter of steel wheels running over rails. No constant vibration from metal touching metal. That is because, once it is moving fast enough, the train is not resting on the track at all. It floats about 10 centimeters, or roughly 4 inches, above the guideway, with no wheel carrying its weight. That 603 km/h run, about 375 miles per hour, was a test record set in 2015. It is not the speed passengers would normally travel every day, but even as a test, it proves something that still sounds almost impossible. A machine weighing hundreds of tons can lift off the ground, stay centered, and move faster than most people will ever travel on land, all without the normal contact between a train and its track. So how do you keep a machine weighing more than 500 tons suspended in the air without letting it tip, fall, or drift sideways? If there are no wheels pushing against the track, what actually moves it forward? And if this technology has worked for decades, why are maglev trains still so rare? To answer that, we first have to look at the simplest idea and why it does not work. The simplest explanation sounds obvious. Put magnets on the train, put magnets in the guideway, face the same poles toward each other, and let the repelling force lift the train. You can feel that effect by pushing two magnets together the wrong way. They resist, almost like an invisible cushion is trapped between them. So why not build a train on top of that cushion? Because balancing something is not the same as keeping it stable. In 1842, British scientist Samuel Earnshaw showed that an object cannot remain stable using only fixed magnetic or electric forces. It may look balanced for a moment, but that balance is fragile. Think of a ball resting on top of a hill. It is balanced, but move it slightly, and it does not return to the center. It keeps rolling away. A train would do the same. If it shifted to one side, the magnetic forces would not automatically bring it back. They could push it farther off center until it struck the guideway. Maglev does not break this rule. Engineers found two ways around its limits. The German system uses constant electronic corrections to hold the train in place. The Japanese system uses motion and specially arranged coils to create forces that guide the train back toward the center. Same problem. Two very different solutions. The German answer was the Transrapid system, the same basic design used for years on the Shanghai Maglev. That train covered a roughly 30-kilometer route to the airport and could reach about 430 kilometers per hour, or 267 miles per hour. But the way it floats is not what most people expect. The train is not sitting on top of the guideway, it is hanging from it. Along the lower sides of the train are metal arms that wrap around the guideway. At the ends of those arms are electromagnets facing upward. When current flows through them, they pull toward the steel underside of the guideway. That magnetic attraction lifts the train and holds its weight. The gap between the train and the guideway is only about 10 millimeters or 0.4 inches. That is less than half an inch. And that tiny gap creates the real challenge. If the magnets pull a little too strongly, the train moves closer to the guideway. As the distance gets smaller, the attraction gets even stronger, which could pull the train into the track. But if the pull becomes too weak, the gap grows and the train begins to drop. So the system has to keep adjusting itself. Sensors measure the gap, and computers change the current flowing through the electromagnets. If the train gets too close, the system reduces the magnetic pull. If it moves too far away, the system increases it. A simple way to picture this is balancing a broom upright on your palm. You do not hold your hand perfectly still. You keep making small corrections, left, right, forward, back, before the broom has time to fall. The Transrapid does the same thing electronically. It does not float because it has found one perfect point of balance. It floats because the control system keeps correcting that balance, moment after moment. and for decades that approach proved it could work at real passenger train speeds. The physics was not the weak point. The train could remain smooth, stable, and fast while floating across a gap thinner than your finger. But a system this precise depends on more than magnets and computers. It also depends on every person and every procedure around it working correctly. And in 2006, that became painfully clear. On September 22, 2006, a Transrapid test train was running on the Leithen test track in Germany. A maintenance vehicle was still on the guideway ahead. The train hit it at 162 kilometers per hour, or 101 miles per hour. 23 people were killed. The levitation system had not failed. The magnets were still working, and the train was still being held in position. The disaster came from human error. Communication broke down, procedures failed, and the train was allowed onto a guideway that was not clear. That difference matters. Even an advanced train is only as safe as the system around it. Germany had already proved that a train could float across a gap of less than half an inch using active electronic control. Japan did not simply replace it with a better idea. It chose a different engineering trade-off. Because Japan must design around earthquakes and ground movement, its engineers wanted much more clearance between the train and the guideway. Instead of floating 10 millimeters above it, their train would rise about 10 centimeters, roughly 4 inches. To make that larger gap, high-speed system work, Japan turned to superconducting magnets. JR Central has spent decades developing this system. The key to producing enough magnetic force across that larger gap is superconductivity. In an ordinary wire, electric current meets resistance. Some of that energy turns into heat, so the current weakens unless more power keeps feeding it. It is a little like trying to push water through a narrow, rough pipe. Some energy is lost along the way. Now cool the right material to an extreme temperature, and the resistance drops to almost zero. Inside the SC Maglev, the magnet coils are cooled to about minus 269 degrees Celsius, or minus 452 degrees Fahrenheit. Liquid helium is used to keep the coils that cold. It does not create the magnetic field by itself. Its job is to keep the material in a superconducting state. With almost no resistance, a very strong current can keep flowing through the coils for a long time with very little energy loss. And that current creates an extremely powerful magnetic field. But strong magnets alone still do not explain how the train stays centered. Along both sides of the guideway are coils shaped like a figure 8. As the train's superconducting magnets move past them, they create electric current inside those coils. That current produces its own magnetic forces. Those forces do two jobs at once. They lift the train and they guide it back toward the middle of the guideway. Imagine the train shifts slightly to the right. The magnetic force on that side changes, while the force on the left side changes in the opposite direction. Together, they push the train back toward the center. The same thing happens vertically. If the train drops too low, the forces become unbalanced in a way that pushes it upward again. That is the key difference from the German system. Transrapid depends on rapid electronic adjustments to hold a very small gap. The Japanese system uses the shape of the coils and the train's motion to create a restoring force naturally. The levitation and guidance coils do not move the train forward. A separate set of powered coils handles propulsion, and we will come to that in a moment. But there is one problem. These lifting forces only become strong once the train is already moving fast. So what supports the train when it first leaves the station? The train has wheels. They are rubber wheels that can retract into the body, much like the landing gear on an airplane. From a standstill, the wheels support the train, while its magnetic propulsion system moves it forward. As it accelerates, the magnetic forces grow stronger. At around 150 kilometers per hour, or about 93 miles per hour, they become strong enough to carry the train's weight. At that point, the wheels fold away. The train rises about 4 inches above the guideway, and the ride becomes fully contactless. When the train slows down to stop, the process reverses. The wheels come back out, touch the guideway, and support the train through the final part of the trip. So even one of the most advanced trains ever built still has to take off and land like an airplane. If the train is floating and no wheel is pushing against the track, what actually moves it forward? The motor is not inside the train. It is spread out along the guideway. This is called a linear synchronous motor. Picture a normal electric motor, the kind that spins inside countless machines. Now imagine cutting it open and laying it flat in a straight line for miles. Powered coils in the guideway keep changing their magnetic polarity in sequence. As that pattern moves forward, it creates a traveling magnetic wave. The train's superconducting magnets lock onto that wave, so it is pulled from the front and pushed from behind at the same time. It is like a surfer riding a wave, except the wave is magnetic and the guideway creates it. To make the train go faster, the system simply speeds up the wave. But that creates another obvious question. If the wheels are not gripping the track, how does the train slow down? The same motor works in reverse. During normal braking, the train's motion turns the linear motor into a generator, converting some of that motion back into electrical energy. Emergency wheel brakes and aerodynamic brakes remain as backups. If power is lost, the train does not instantly drop. At high speed, the magnetic forces remain strong enough to keep it levitating while it slows down. With no wheels rubbing on rails, the biggest force left to fight is the air. At extreme speed, air resistance rises sharply, which is why the train has a long, needle-shaped nose. It helps the train move through the air more smoothly, with less noise and less energy loss. If Maglev works this well, why is it not everywhere? The answer has less to do with physics than with what has to be built around the train. A conventional high-speed train carries most of its key machinery on board, and in countries that already have high-speed rail, much of the surrounding system already exists: tracks, stations, power equipment, and maintenance facilities. A Maglev cannot simply be placed on that network. Its motor is spread along the guideway. The levitation coils, guidance coils, power equipment, sensors, and control systems also have to be installed across nearly the entire route. So building one does not just mean buying a new train. It means building a completely new transportation system. Japan's Chuo Shinkansen shows the scale of that challenge. The first section, from Shinagawa in Tokyo to Nagoya, is about 286 kilometers, or 178 miles long. More than 80% of the route will run underground or through tunnels, and the approved construction budget is 7.04 trillion yen. Meanwhile, conventional high-speed rail has spent decades improving. Some trains already operate at around 350 kilometers per hour or 217 miles per hour using networks that countries have already paid to build. That makes Maglev a difficult economic choice. It is faster and technically proven, but the extra speed only becomes useful after governments and companies commit to an entirely separate guideway, power system, stations, and maintenance network. The train is not the main problem. The price of everything around it is. 603 kilometers per hour, a train floating 4 inches above its guideway, held up by superconducting coils, chilled close to absolute zero, and pulled forward by a magnetic wave running through the track. It sounds impossible, but it works. Maglev is not a failed invention. Engineers know how to lift the train, guide it, accelerate it, and bring it safely back down. The real obstacle is everything around it: a dedicated guideway, powered coils, control systems, new stations, and a maintenance network. That is why Maglev can break speed records without becoming common transportation. It is not magic. It is physics. Physics made Maglev possible. Economics kept it from becoming ordinary. Until the cost of building that new world comes down, the future of rail may keep arriving at 603 kilometers per hour, one route at a time. If this video helped you understand Maglev, hit like, subscribe for more technology explained simply, and tell us in the comments, would you ride a train moving at 375 miles per hour?